Ancient mysteries, whispers in the darkness, the nature of light, a mystery since the time begins. Ancient civilization gazed at the stars. They wondered about the sun's brilliant rays. What was this eternal substance? How did it illuminate the world? Some believed light was just a divine animation. Others thought it was a tiny particle streaming from our eyes. The answer remained elusive. The universe had its secret closed. The Greek, with their thrust of knowledge, ventured close. They observed light executing behavior. It reflected off surfaces. It bent when it passes through water. These early philosophers laid the groundwork. Their observation would echo through the edges. The stage was set for the scientific revolution. Lights to nature was to unmasked. Isaac Newton, a giant of science. He revolutionized our understanding of the cosmos. His laws of motion explain the dance of particles and planets. His theory of gravity unveils the true design of the universe. And in 1704, he turned his brilliant mind to the enigma of light. His book, Optics, sent a shock wave to the scientific world. Newton proposed a bold theory. He said that light was not just a ray, it is a stream of tiny weightless particles, and he named it corpuscles. These particles traveled in a straight line at unimaginable speed. Newton's cosmos theory was elegant, simple, and powerful. But Newton was not alone. In the Netherlands, another scientific giant offered a radically different view of light. Christian Huygens, a brilliant mathematician and astronomer, had been pondering the nature of light. He too had observed its curious properties, but his conclusion differed drastically from the Newton's theory. Huygens believed that light was not just a particle at all. It was a wave, just as a sound wave traveling through the air. Huygens proposed that light waves travel through an invisible medium called luminiferous ether. But Newton argues that light waves are like particles would spread out and interfere with each other, and this caused diffraction, a phenomenon where light bends around obstacles. The battle lines were drawn on. One side, the Newton, the champion of particle theory. His reputation was unparalleled. His corpuscles theory was elegant and powerful. On the other side, Huygens, the proponent of the wave theory. His idea was radically challenging the established theories. The scientific world watched with bated breath. Which theory will prevail? The debate dragged for over a century. Each side presented confident. Each side refuted the other claims. The stakes were high. The very nature of light, one of the universe's fundamental forces, hung in the balance. In the early 19th century, a crucial experiment tripped the scales. An English scientist, Thomas Young, established a simple but ingenious experiment. He shone a beam of light through two closely spaced slits. If light were particles, as Newton claimed, then two bands should appear on the screen behind the slits. But that's not Young's observed. To everyone's astonishment, a series of light and dark bands, an interference pattern observed on the screen. Interference in the hallmark of wave. Young's experiment seems to deliver a fatal blow to the Newton corpuscles theory. The journey of understanding light was about to take a dramatic turn. Just when the wave theory seemed prevented, a new puzzle emerged, challenging the very fundamental of our understanding. In the late 19th and early 20th century, scientists discovered the photoelectric effect, a phenomenon that defined the existing wave theory of light. When light shines on a certain metal, it knocks out the electrons from that metal and create an electric current. This was a groundbreaking observation, and this phenomenon could not be explained by the wave theory alone. The wave theory suggested that light energy was spread out, but this effect required a different explanation. In 1905, a young Einstein came to the stage to explain this light-challenging QO. In 1905, a young Albert Einstein stepped onto the stage ready to challenge the status quo. He proposed a revolutionary idea that would change the course of physics forever. He argued that light not only behaved like as a wave, it also behaved like as a particle. This dual nature of light was radically departure from the existing light theories. These particles of light, later called photons. Einstein's explanation of photoelectric effect, based on the idea of light quantum, earned him the Nobel Prize in the physics in 1921. His work made the foundation for the quantum mechanics, a field that would change and revolutionize our understanding of the universe. Discovery of photoelectric effect and Einstein explanation sent shockwave through the scientific world. These groundbreaking discoveries challenging the very foundations of the classical physics. Light, it seemed, was not confined to the neat categories of particle or wave. It defined the conventional wisdom that had dominated scientific thought for centuries. It could be both, depending on how it was observed. This duality means light to show properties of particle in some experiment and properties of wave in others. This revolution marked the dawn of a new era in physics, quantum mechanics. Scientists around the world began to explore these strange new territories, uncovering phenomena that define everyday notations. Quantum mechanics, with its strange and counterintuitive laws, reveals the universe to be far more bizarre and wonderful place than we had ever imagined. It shows at the smallest stage the universe operated in the ways that fundamentally different from our microscopic experience. Light's dual nature, once a baffling paradox, became a counterstone of this new understanding of the quantum realm. It was a key place in the puzzle that helped scientists to develop a more complete picture of a subatomic world. The wave-particle duality, as it come to be known, was not a bug in a system, but a feature, a fundamental aspect of a reality. The mystery of light, however, is far from solved. Despite centuries of studies and counties of experiments, it continues to baffle and confuse the scientists, while we have come to accept the light's dual nature as the fundamental of quantum mechanics. But many questions remain unanswered. This duality, where light can be a wave or a particle at the same time, challenging our understanding to the real universe. What is the true nature of wave functions that describe the behavior of quantum particles like photons? This wave function, a mathematical description, holds the key to understanding quantum behavior. Yet, its true essence eludes us. How does light choose whether to act as a wave or act as a particle in a given situation? The famous double-slit experiment revealed this duality, but the underlying mechanism remains a mystery. And these are just a few profound questions that challenge and confuse the scientist till today. The quest to understand the light is not just about understanding the light itself, but about the fundamental principle that quantized our reality. The study of light, once a quest to understand a single phenomenon, had led us to the very heart of reality, revealing complexities and paradox that were previously unimaginable, forcing us to comfort the deepest mysteries of the quantum world. As we delve deeper, we find that each answer only leads to more questions, perpetuating the cycle of discovery and wonder. The study of light is a testament of power of human curiosity and ever-evolving nature of scientific understanding, from ancient mysteries to the modern quantum theories. Our quest to comprehend it, light, has illuminated not only the physical world, but also the boundless capacity of the human mind to explore and unreveal the universe's most closely grounded secrets. Light, the very essence of our ability to perceive the worlds around us, remain an enigma, a source of endless world and inspiration.